Why does inflation, 10 raised to minus 36 seconds after the Big Bang, still have a high uncertainty, even after cosmic microwave background radiation imaging? Also, is there eternal inflation not just at the Big Bang? All right. So, what is inflation? What is this cosmic cosmological inflation? And does it not work? I mean, does it have a high uncertainty? I'm assuming what he's asking by what he means by high uncertainty is that we don't have evidence of that. Is that so? So, it's a long answer. So let's take it step by step. First of all, cosmic inflation is part of the Big Bang theory, but it was not part of the initial Big Bang theory. The initial Big Bang theory was based on a couple of rules, a couple of principles. First of all, that the rules of general relativity are is the framework. General relativity is the framework set of rules that governs the universe. That was the first uh, consideration of the Big Bang theory. And secondly, the Big Bang theory was about taking the data into account. Whatever data we have data, we have observational evidence that the galaxies are all receding, they are all moving away from us, and they are moving away from us at speeds that are proportional to their distance from us. So the further away the galaxies are, the faster they are moving away from us. So that's the kind of i- information that we had. So based on this, what we saw is that if we take these things into account, then uh, certain logical considerations come out of this. So, for example, as per general relativity, if you fill the universe with matter, which we know is there, matter and energy, light and radiation and all that, and if it is reasonably evenly distributed, as we know it is at the largest scales, then that universe that you are constructing in this manner, it will not remain static. Like the Fred Hoyle, Janet Narlikar theory, steady state theory, it won't remain static. It must either expand or it must contract. Okay, so it's either an expanding universe or a contracting universe based on this, and we know it's an expanding universe based on observational evidence. And then what you do is you go backwards in time, you extrapolate this backwards in time, and that was the big idea of the Big Bang, the Big Bang theory. So the Big Bang theory makes a number of predictions, okay, and I'm not going to go into the details of that, but these predictions have been verified. And that's why the Big Bang theory, what we call the Big Bang theory, is the theory that works. It is the best theory that we have right now. Okay, all the other theories, whichever they are, they kind of have faltered here or the other, but the Big Bang theory works. But there are certain predictions of the original Big Bang theory that did not work. For example, look, once the Big Bang happens, this alleged explosion, it's actually an expansion of the universe. But once this happens, you have the universe, the various components and parts of the universe that move apart from each other. And this happens over billions of years. So you have large areas of the universe that have not been in contact with each other for 13.8 billion years, let's say. So, therefore, if you look in different directions in the universe, you should see different temperatures. Different parts of the universe at different temperatures, right? Logically makes sense, but it's not there. It's all uniform, same temperature everywhere. Why is that? And then, as per the Big Bang, there should be in the very early uh, part of the universe, the very early let's say time period of the universe, there should have been the production of exotic weird particles like magnetic monopoles, etc. Well, where are they? We have never discovered a single magnetic monopole anywhere, right? And then the universe should have spatial curvature, it should be curved, but it's a flat universe that we see. What do I mean by a flat universe? The flatness problem. Why is the universe flat? What do I mean when I say that the universe is flat? See, let's say you have a ball, okay, a spherical object. On a spherical object, if you take 3 points, it should draw a triangle, right? Yes, should draw a triangle. Now, the geometry that we learn in school, it says that when you have a triangle, the sum of the three angles is what, 180 degrees? 180? I think it's 180, right? But in curved space, it could be more than 180 or it could be less than 180, depending on the curvature, if it's positive or negative curvature. But what we see is that it's essentially flat space. The universe is flat. If you draw a triangle, three very far apart objects, you're gonna see the sum of the angles is 180. So you have a flat universe, there is no measurable curvature. So these are the problems with the Big Bang theory, and that's where inflation comes in. So inflation was proposed by Alan Guth in 1979, 1980. I think the paper came out in 1981, but it was proposed. The idea popped into his head in 1979. Okay, so inflation is what solves these problems. So inflation is this state of the universe that is before, well, it's a very very initial part of the Big Bang, essentially before the Big Bang, you could say. So you have a very early universe, and then there's inflation, and that's kind of the Big Bang. So in this inflationary state of the universe, the dominant form of energy, according to this theory, wasn't matter, it wasn't radiation, it wasn't all of that. It was the dominant energy was inherent to the fabric of space itself. Okay, space itself was full of energy, and it had a tremendously high energy density. Okay, and this incredibly high energy density that was inherent to the fabric of space itself, that is what caused the universe to expand rapidly. And it was not just rapid expansion, it was superluminal expansion. The fabric of space or space time expanded faster than the speed of light itself. So you can break the speed of light if it is space time itself that expands. So that can expand at any speed. So that was the thing, superluminal expansion. Okay, and so this caused the universe to expand ridiculously rapidly, superluminally rapidly, and this caused the universe to be stretched so large that it essentially became indistinguishable from flatness. Okay, and because it expanded so rapidly and so on, so that's why if you look at the universe in different directions, if you look at various parts of the universe, then we will see the same properties everywhere, uniform properties of the universe everywhere, because they all originated in a from a previously connected state in the very beginning. Okay, and also when inflation ends, okay, inflation is not something that goes on forever, it ends at some point in time, and it did end. So when this ended, all this energy that was inherent, that was part of the fabric of space, it transformed into matter and antimatter and radiation and whatnot. And and by this process we also avoid the production of exotic particles, magnetic monopoles, etc. But magnetic monopoles could still exist, but it's just that we have not found them. Maybe they are stretched, they are they are spaced very very far apart and so on. So that is inflation. It solved the problems of the Big Bang, of the original theory. So it is kind of an addendum to the Big Bang theory. It is something that we attached on top of the Big Bang theory. But yeah, it makes predictions that many of these predictions have been verified. So quantum fluctuations, for example, it says that quantum fluctuations during inflation, quantum fluctuations is, it comes out of quantum field theory. uh, you can kind of violate the Heisenberg uncertainty principle, as long as you do it within a certain time frame and so on. So quantum fluctuations during this period of inflation would produce the seeds of density fluctuation. So you have, if you look at the universe at the largest scales, it's kind of homogeneous, isotropic and all that. But if you look at it at smaller, more local scales, you have, you know, fluctuations of density. You have galaxies and clusters of galaxies in some places, and some places you have voids, there's nothing in there except for maybe interstellar medium, protons and electrons and all that. So why is it like that? It's because of the fact that the quantum fluctuations in the very early universe during the inflationary phase, they produce the seeds of today's density fluctuations. So all of those over densities, they could also have produced micro black holes and all, but that's a different story. So those fluctuations, quantum fluctuations in the very early phase during inflation, they eventually gave rise to all these regions of high and low density and galaxies and all the structure that we have in the universe. Okay, and one of the predictions of inflation is that the universe should should be filled with we know we have cosmic microwave background radiation, CMBR. We have the CMB, cosmic microwave background, which is the background of the electromagnetic waves. It's light, it's photons. Similarly, there should be a cosmic gravitational wave background. Primordial gravitational waves should be all around us. The universe should be filled with these primordial gravitational waves. And these primordial gravitational waves should actually imprint themselves on the cosmic microwave background as something that's called B modes, and there was a false positive detection of this, the bicep 2 experiment. Yeah, there was a famous video out there on YouTube and so on. So that's not yet been proven, but a number of things have been proven. And obviously flatness, the universe should be almost nearly flat, but not quite perfectly flat, and a little bit of that could be there. So that is what inflation is. So it is not something that has a high uncertainty. Lots of evidence of inflation has been found. It solves the problems of the original Big Bang theory. It improves it significantly, right? So that's what it is. Eternal inflation, not just a Big Bang. Well, in that we have to go into delve into different theories. Maybe there is inflation that goes on even eternally and so on. But overall, the point is inflation is the best theory that we have if we attach it on top of the Big Bang theory. It essentially accounts for the state of the universe the way we see it today. All right.